Hello everyone, and welcome to watching this video. Today I'm going to talk about my honors capstone project at the University of Michigan College of Engineering. My name is Mitch Miller, and this capstone was advised by Professor Brian Gilchrist. And my project I'm going to be talking about today is a derivative of the mighty Cubesat program, and is the integration of geophysical models for an electrodynamic tether propulsion modeling environment. So the best way to discuss this project is to discuss the motivation behind it. And what it really boils down to is the economics of spacecrafts. And it's very complicated, and you'll soon see that. Because of launch cost of getting a satellite into orbit, these cost on the order of thousands of dollars per kilogram to put a satellite into a low Earth orbit. Low Earth orbit is the most common orbit for satellites to land in, and about 75% of satellites that are operating today are within that region. Unfortunately, this is a very big price tag, and there's a couple different ways to combat this. Traditional satellites are very expensive to produce just because they're very large, as you can see in that left image. And they weigh several thousand kilograms. If you add that on top of the several $1,000s per kilogram price tag, you're looking at a very expensive spacecraft to produce. Additionally, because it is so massive, what happens is we're forces this more money, more problem issue. Companies and agencies that are developing a satellite will want to get the most for their money, so they end up packing as much instrumentation as possible into a single massive satellite, so you don't have to produce multiple satellites because it is so expensive to do so. You'd rather just produce one. This has a couple downsides for instrument principal investigators, as they have less flexibility choosing ideal parameters for their missions, as well as it increases the complexity of the satellite as a whole significantly. So there became this different idea of, instead of creating this massive satellite that holds several instruments, why don't we scale everything down into a small sat? And what happens, as you can see in the image to the left, is we can compress a satellite down to the size of a loaf of bread or even smaller. So the satellite you see on the left is a 3U CubeSat, and the U is a standard measurement that is 10 by 10 by 10 centimeters. And this is made possible by the scaling of modern electronics. The analogy that we like to draw is, think about the first computers and how they required an entire room. And now your smartphones can do all those capabilities and much more as something that can fit into your pocket. So the scaling down of electrical components is what's made small sats possible to be compressed down into a small bus that is very low mass and thus very low cost to get into orbit. And this is where this substantially cheaper idea comes from. The reduced complexity of small sat is significant over a larger traditional satellite, as well, as it does not require all the major systems that are associated with having a massive satellite, especially in the realm of attitude control. That can be done much easier within a CubeSat, since it's a very low mass instrument. Another major advantage for science operating on small sats is that we're able to have constellations of satellites set up much more easier because they are much more cheaper to produce. And you can have measurement distinction over the temporal and spatial space. Now, what this means is that with the satellite constellation, if there is an interesting phenomenon that we're measuring in our science realm, we can tell if that was a temporal thing, such as a solar flare that's only happening at one distinct point in time, or something that's happening spatially, such as the Southern Atlantic anomaly, where radiation is more likely to damage a spacecraft and is a point in space above Earth. So having a CubeSat constellation is able to have distinction between this. The other thing to keep in mind as a big motivator for this project is space is very complicated. We typically think of space as a pure vacuum, but this is actually false. Most spacecraft operating in low Earth orbit are actually in Earth's atmosphere still. in a region called the Ionosphere. And what this is, it's a region that we colloquially think of as a soup of electrically charged electrons and ions that are very high energy, but very sparse and very spread out. It's not a high density. There is a big downside to this, and that is that orbital drag becomes a big issue with satellites operating in this region because there is still atmosphere. With the atmosphere, as you can see in the bottom image, is that with each orbit you are going around Earth, you're going through this atmosphere, and that's going to decay your orbit and bring you closer and closer down to Earth's surface. This becomes a major issue with satellites once they reach an altitude that's that's a much more dense atmosphere than what they've been operating in, and they begin to fall out of orbit and disintegrate into the atmosphere and become decommissioned satellites. This is additionally a really big deal for small sats as compared to traditional satellites, since small sats have a very high surface area to mass ratio. The analogy that we like to draw is if you're driving a car on the freeway and you throw a leaf out of the window, that leaf and your car both are experiencing the same drag force, but that drag is going to affect that leaf much more significantly than the car because it has a much higher surface area to mass ratio. The same idea applies to small sats in orbit, so they only are able to stay in orbit for a time span of about 6 to 18 months, whereas a traditional satellite, a larger, more massive satellite, operating in the same orbit can operate there comfortably for years with little orbital decay. So at the University of Michigan, what we are trying to do is turn that problem of this small amount of atmosphere in space actually into an asset instead of being a disadvantage for small sats. The main thing to keep in mind is that, as I said earlier, the region that we're operating in is in a soup of plasma ions. So there are electrical charges that we can use to our advantage. And what we're using is the concept of electrodynamic tether propulsion. So in this image, you can see in the bottom satellite, if we bias that satellite to a very high positive voltage relative to the ionosphere, we can actually attract electrons to collide with that bottom spacecraft, make them travel up a electrically conductive tether to an upper spacecraft, and re-emit those electrons back into the ionosphere to complete an electrical circuit. What happens is that current acting through that tether creates a Lorentz force that can counteract the drag force to create propulsion. And this is very important because it allows these spacecrafts to get into orbit without having to bring their own propellant. So this is a fully propellantless propulsion system. And this is novel since without having to worry about carrying your own propellant, you can keep on miniaturizing your spacecrafts to save on launch cost and space and complexity, while still being able to operate your satellite for theoretically infinite timescales, limited to how long the materials can last in the space environment before degrading. So this is an exciting thing that we're doing at the Mighty Cubesat program. We're a student-run organization under Professor Brian Gilchrist, and our concept is to take the idea of an electrodynamic tether and bring it to reality. Electrodynamic tethers have a very low technology readiness level as of current. However, it's our goal to try and raise that. In these images, you can see our Mighty 1 spacecraft, which we actually deployed to orbit earlier in this year in January 2021. And we are operating as a Pathfinder mission to collect data for our Mighty 2 spacecraft, which is an upcoming mission that is in the preliminary design phases currently. So with the Mighty 2 program, there's a big difference between Mighty 1, and that is this rigid deployable boom that you see in this image is replaced with the electrodynamic tether. Mighty 1 is designed to gain science data so we can go into the full implementation of an EDT in Mighty 2. The big problem again is that space is still very complicated, and we need to come up with a robust and capable modeling environment to actually design our Mighty 2 spacecraft. This is because of the electrodynamic tether is very complicated with regards to electrodynamics and non-rigid body mechanical motion, which both need to be considered to develop a spacecraft that will actually operate properly, especially with this tether that's free floating in space. So to be able to do that, it was my goal to create a modeling environment that we can use. And what I did was I used the Tempest Software, which was an early electrodynamic tether propulsion and energy harvesting tool first developed in the 1990s. And it was my goal to bring that to the 2020 standards of today. So this is a very outdated tool. Its last major update was in the early 2000s, but it's a very valuable tool for the EDT community. And my objective was to take the geophysical and solar models that were embedded inside of it, update and reevaluate them with a critical analysis of the science that we know of today, and to create an accurate modeling environment that we can use for the Mighty 2 spacecraft and broader for the EDT community. The next steps for this project are, it's a very work in progress project as of current. Because of the COVID-19 pandemic and some unforeseen issues, we've had some delays, and this project is being extended into the summer of 2021 and possibly into the fall of 2021, depending on the progress that we make. The next steps is to have a collaboration actually with several other universities that are active in the EDT community. These include Penn State, York University of Canada, and the University of Carlos III in Madrid, Spain. Within these communities, we are attempting to verify and validate the updated Tempest software with these different stakeholders at these different universities. There do exist about 2 other different EDT modeling softwares that are in circulation today. However, it's our goal within these 4 universities, including the University of Michigan, to go ahead and critically evaluate and see the strengths and weaknesses of the models against each other to iteratively make each model even better. Once that is done and we feel comfortable that our models are good and accurate to be able to use in simulating a real spacecraft, we're going to move forward with our partnership with NASA's Jet Propulsion Laboratory with using their Dynamics and Real-Time Simulation Software, or DARTS for short, to integrate mechanical non-rigid body motion within the electrodynamics models of Tempest. The idea behind this is it's a very complicated mission for Mighty 2, and we need to be able to consider both the mechanical dynamics and electrodynamics. And the DART software package is something that is very capable for space missions with modeling the complex mechanical motions. This is also bolstered by the fact that the DART software is easily integratable with applications like the Tempest code as it gets updated into a new format. As a brief summary to talk about what we learned in this brief presentation is that space missions are driven by both economical and physical limitations, and these are the major drivers for the space industry currently. Small sats have a very great economical advantage over larger traditional satellites because of their very small, compact, and simple design. But because of the small amount of atmosphere in the ionosphere where these satellites operate, these small sats have significantly shorter mission lifetimes, and that needs to be addressed. And as these small sats become more and more widely used, we need to figure out a way to have an advanced propulsion system that can actually address these concerns. That's exactly what we're trying to do with the Mighty program at Michigan, to demonstrate EDTs as a viable on-orbit technology. And the steps that we need to do this for the 92 mission is to have an advanced modeling software to actually prove out these systems virtually before sending them into space. We want to make sure we do this so we actually have a system that works and is functional, as opposed to something that could fail due to something that can be easily avoided by having a modeling software. So I want to thank you today for listening, and to briefly go over a handful of common questions if you were to watch this in a live presentation. First question is, how did I get involved in this project? So I'm actually a 4-year member of the mighty Cubesat program. I joined as a freshman at Michigan and have continued throughout my senior year here. And the way that I got involved is through the multidisciplinary design program. I was able to apply and onboard into the team through that program, and that is how I was able to meet Professor Gilchrist and create this offshoot program from being an active member throughout my time at college. Second question is, did I accomplish what I hoped to with this specific program? And my answer to that is we're not quite there yet, but this is a work in progress. I'm still dedicated to this project and hope to see it through to create this modeling environment. We ran into some unforeseen issues that really delayed progress, especially within the COVID environment, and Penn State was also a very big driver within this, since we did not want to bifurcate the code. We wanted to have a consistent background. So having some institutional issues with communication between the two different universities did make this a little bit more difficult to move forward with. However, I'm proud with what we've been able to do currently. We're getting there, and the end is near. So it's a work in progress, but I am hoping to be able to accomplish this within the next few weeks over the summer. Third question is there anything you would do differently? My answer to this is to start early. So that would be my advice to any other honors students who are planning on doing a research capstone. It's these unforeseen issues are issues that will happen, but you can't predict them. So my advice is to start early to identify them and address them early. So again, I want to thank you for listening to this presentation. I hope you enjoyed it. If you have any questions, please feel free to leave them in the comments of this video. Thank you.